if we are applying a force P of 300 newtons on this system, if we want it to not move when we apply 300 newtons, we're looking for the minimum coefficients of friction between the block and the spool and the ground. So we want to find, I called it mu A and mu B, since A is that contact point between the block and the spool, and B is between the spool and the ground. So the minimum values of mu A and mu B before motion would occur. Here we're given that we know what the applied load is, so it's a little bit different than the types of ones we've been looking at. We're applying a load of 300 newtons. We know the mass of the block C is 50 kilograms. And the mass of the spool was 40 kilograms. Right. The height, the length of the block, we don't have information about, so we can't see anything about tipping or if it's going to try to rotate in that constraint. But we do have some of the information about the spool that we will use. So the spool is going to be treated, we can treat like a rigid body, but the block we'll just treat like a particle. We don't know where lengths or normal forces are going to be located on it. In our free body diagram step then, we'll have that block C, and we'll have the spool. So I'll draw a free body diagram for each of them. For the block at C, I know its mass, therefore I can find its weight. So I have the weight force acting on the block of 50 kilograms mass, means that 491 newtons down will be its weight. There's going to be the normal force at A. That will be easy to draw here, so I'll start there. I call that NA. That has to be up. Now the wall, this is kind of in the modeling part going to be a little bit tricky on how we want to do this one. Right, we have to see, is it kind of constrained tightly between those two walls, or it's a little bit loose, so that if we're pushing it to the left, it's not really in contact with the right anymore, or if we're pushing it to the right, it's no longer in contact with the left. And actually for this, it doesn't matter too much for our solution. So I'm going to model it that it is only going to be touching one wall at a time. It's either touching the left wall or the right wall. But we're not necessarily sure right now which is happening. I'm going to come back to this one for which wall is it touching, because we would predict that if it's being pushed to the left, then the left wall is in contact. If it's being pushed towards the right wall is in contact. So there'll be another normal force I'll come back to, and what other force is going to act then on block C. There will be friction there at this surface that we want to account for, but none on the vertical surface. Again, I'll come back to the direction of it until we think about how the spool is moving, which will make it a little bit more obvious maybe what direction the friction should be. This is not done yet. I'm going to circle back to it. And I can start to draw what's happening to the spool. So the spool has a center at O. 0.2 meters to that inside part of the spool where the force is being attached, and then 0.4 to the outside diameter of the spool. I'm applying that force P of 300 newtons. I have the normal force in the opposite direction, so the spool pushes up on the block pushes down on the spool. And I'll have that friction force, which I'll come back to also in a second. I have the weight of the spool acting down. The spool mass is 40 kilograms, so it weighs 392 newtons. It's resting on the ground. The ground pushes back up on my spool with some normal force I'll call NB. So now is the part where we have to think of the different ways that this can move. Previous examples, kind of all the motion, the direction of the friction would be the same no matter what. We have to think here, if we're pulling on it with 300 newtons of force, how can motion occur in our system? Because again, we're looking for the friction forces so that no motion is going to occur. Yeah. One possibility is that we start to pull on the spool, and then it would rotate counterclockwise when we pull on the spool. So if that's the case, if it's rotating counterclockwise, we have to use that information to think how would we draw the frictional forces. So if it's rotating counterclockwise, what's the friction force going to be doing at, let's say, B first? The force is only going to be along an axis, though. So it's not, the friction doesn't act like a twisting. Right, we have to think about this point on the spool. If we're rotating counterclockwise, this point on the spool wants to move to the right relative to the ground. So if it wants to move to the right, then the friction force is going to oppose that motion and be to the left. Again, under the circumstance where we pull on it and it starts to rotate, the top of the spool wants to move to the left relative to the block at C. So in this case, the friction force would be opposing it and actually be to the right. If FA is to the right in this picture, then FA is to the left in my top picture. If the friction force is pushing this to the left, then I would presume that the normal force would be counteracting that and pointing to the right. Right, so these were decided for us. The normal force, we'd have to make sure the math works out. Remember, when we solve these, normal forces must be positive and friction forces must be positive. This was all modeled under the circumstance that we pull on it and it starts to rotate. But how else could there be motion in the system? Right, we pull on this and the whole thing without rotating slides over. So the difference is going to be, and we'll get to this in a minute, is now this point still moves to the right relative to the ground. But when we pull the spool, this point actually moves to the right with respect to the block. So actually there's a difference not only in what the math is going to do, but the free body diagram will actually be different in the second scenario than the first scenario. Because this point A moves to the right relative to the block rather than the left relative to the block. So it's a little bit more complicated than the previous examples where really it was just changing some equations. This changes the free body diagram, which actually will change the equilibrium equations too. But we'll start under this premise that it rotates. From the block, again, I can't get a moment equation. I don't have enough information, but I can some forces x and y. In the x, I'm assuming the normal force points to the right, and from the drawing, FA points to the left. In the y direction, I have the weight down, and I have the normal force at the bottom surface up. And that will tell me that the normal force at A is 491 newtons. I can't get a moment equation, so I'll move on to my second picture to get the rest of my equilibrium equations here. If I start with the y direction here, I have my NA down, the weight down, and the normal force of B up. This tells me that the normal force at B is 883 newtons, and it turns out to be the sum of the mass or the weight of the block and the weight of the spool. In the x direction, from the picture, I'll have FA minus FB plus 300. And on this one, I can take the sum of moments, and I'll just do it around the center of the spool, that point O there. The normal forces are going to act through the center of the spool, so they are not going to contribute to the moment around point O. I'll have a moment caused by this applied load of 300 newtons that is 0.2 meters away, and that is going to be counterclockwise. From the friction force on the top, that's 0.4 meters away, that'll be a negative 0.4 times FA. And then a moment at the bottom that's also going to be going clockwise. so that's FB times 0.4. Three equilibrium equations from the spool, two from the top here. And unlike previous cases that we went through, these 5 equations only have 5 unknowns. So we are able to solve for them before we get to applying anything being on the verge of slipping or being on the verge of tipping or anything like that. Again, counting it up, we have NC, NA, FA is 3. We have NB is 4, and we have FB is 5. So right now it's solvable. And if we go through these, if we look at equation 5 and equation 4, there are, between those, FA and FB are unknown. I can solve for what those friction forces must be to keep this in equilibrium. I'm going to solve FB first. If I solve this for FB, I get 225 newtons. And if I solve it for FA, I get negative 75 newtons. So that was using equation 4 and equation 5, and then I can find the rest of this information if I want. Right away here, I know I'm going to stop because I got that FA was a negative number, negative 75 newtons. Friction forces cannot be negative. That would mean that it would be sliding to the left, but the friction force would also be going with it towards the left. So this tells me that negative 75, I can't have a negative frictional force, which means that my modeling is wrong or this motion is not going to be possible. So this negative 75 tells me that the rotation of the spool is not possible. It would take a negative friction force in order for this to actually rotate counterclockwise when I pull with 300 newtons of force. This scenario is not feasible to happen, but what I have to actually do is change my free body diagrams. So I'm going to get rid of this. We ruled this out as a possibility. I actually want to go back here and modify the free body diagrams. It can't rotate, so that means that it actually must be sliding, since of the 2 possibilities, the first one can't happen. If we're saying that the whole spool slides to the right, FB is still pointing to the left because that point is still moving to the right relative to the ground. But if the whole spool slides to the right, as I said earlier, point A is now moving to the right with respect to block C, which means that FA should actually be pointing in the other direction. If FA is actually pointing to the left in this picture, then it should be pointing to the right in this picture, which means that the normal force should actually be from the right wall to balance that out in picture C. The direction of that normal force, NA, hasn't changed and NB hasn't changed, but it did change the 2 free body diagrams a little bit. Because the free body diagrams have changed, we have to go and fix our equilibrium equations to reflect that change. So there's nothing wrong with making an assumption, getting our negative friction, but unlike before where like in a pin reaction, if we got a negative number, we could just kind of march along and it would be okay. This actually changes the problem and we do need to go back, redraw it, and resolve our equilibrium equations. So going back through here, we have to look at what changes. Here, this is now pointing to the left. FA points to the right. It really doesn't change the relationship between the normal force and the friction force, but that will change. Equation 2 is unaffected because NA is still up, 491 is still down. Equation 3 is not affected. Our normal force B is still the same. Equation 4, FA now points to the left, so that needs to be negative. FB is still to the left, so that remains negative, and the 300 is still to the right. And if I come down here to equation number 5, because FA now points to the left, then FA is going to be exerting a counterclockwise rotation around O, so that will become positive. So actually, if I go and resolve this, I get here FA is positive 75. So it did just switch sign in this case, but now everything is pointed in the right direction. And for FB, I get a 225. I have a positive friction force. I have a positive friction force. So that's the first check to make sure this is at least a feasible situation. I can use that information now to find NC. Make sure that that normal force is going to be positive. I get NC is 75, positive 75 newtons. I can solve for, I already know NA and I already know NB, so I have all 5 unknowns that I have so far solved for from the equilibrium equations. So at least force-wise, I'm done. So where do I go from here? And everything that needs to be positive is positive. So where do I go from here to solve the rest of the problem? This was not one that was simply asking what are the forces. If we go back to the find here, we need to find what must the minimum coefficients of friction be between the block and the spool and the ground, such that when I apply the 300 newtons, it's just not moving. What we can say is, for this to just be on, if we were looking for what the minimums have to be, we can say that this whole system is just on the verge of going into motion, and that will give us the minimum values these frictions would have to be. Now I can add those additions, that the friction force at A is at its maximum value, and the friction force at B is at its maximum value as well, simultaneously. Because they would both have to be at their maximum simultaneously for the spool to be able to slide to the right. I know FA is 75. Mu A I don't know, but NA I know is 491. So the minimum the coefficient of friction has to be at A, or could be at A, is 0.153. And down here, the friction force was 225 newtons times mu B times the normal force between those surfaces was 883. So from equation 7, the smallest that mu B can be is 0.255. These are the smallest the coefficients can be because it's just on the verge of moving here. If either one of these is larger than that, it's still not going to be in motion, but it would just be true that FA would be less than or equal to mu A times NA, or FB was less than or equal to mu B times NB. What we're testing here is kind of that worst case scenario. They're both just about to give out, and the spool is about to slip to the right under these conditions.